So Chloe, so I went over a couple things. I went over some stuff on the lab, quick stuff, not that important, as well as I talked about a group chat that apparently already exists. And what else did I talk about? I talked about something else. Pumpkin chunking, yeah, pumpkin chunking's Tuesday, if you want to do that. All right, but this is the actual heart of the lesson right here. So we're going to talk about X versus T, V versus T, and A versus T graphs. Okay, you'll notice in every single one of those that time is on the independent axis, and this is the reason why even when it wasn't supposed to, I was forcing time to be on that particular axis, and so you get this consistent thing throughout this shape that hopefully makes sense. Okay. All of what we're about to do is essentially going to be done in a sketch. You are not going to need to like do this by hand. When it comes to sketches in here, what I expect is something I've said before. I don't want you to take forever on it. It's not an amazing drawing. I don't want you to take no time on it. Okay. I think kind of just like throwing something on the page real fast is going to make it look not so great. Now, here's the good news. We already had labs on both of these. What does the X versus time graph look like? Just discuss quickly in your group after I'm done here. In the toy car lab. And what did the X versus time graph look like on the ramp lab? Discuss quickly, sketch it down. And we'll discuss. Go ahead. That's not right. All right. What's the car lab look like? Linear, correct. Why? Can you speak a little? You're 100% right so far. Can you speak a little bit more to that?
Both X and T increase at a constant rate.
There's probably the best way to put it right there, because that's what constant velocity means, right? Here's a good thing. Here's a good trick for the test, because this is definitely a question that regularly comes up. Hey, what does 8 meters per second mean? This one should hopefully be. Okay, let's do this actually. Let's do this here, because this will be good. I think one should be easy, one should be a little bit harder for some people, but okay. What does 8 meters per second mean? First question. Second question, separately, what does 8 meters per second squared mean? Discuss quickly in your group. Oh, I didn't finish my first sentence. What shape is it? Parabolic. All right, hearing not that much conversation. Understand there's a couple layers to this. When I say what does it mean, the first student kind of wants the first layer is they want to name it. That's fine, but that's not the layer I want you to stop at. So let's do that first, okay? Because if I say 8 meters per second, name what that is. Velocity, correct. And the next one is great. Now, if you can do that, okay, hopefully you have the answers to these kind of intrinsically already, but if you don't have the answer to what I'm going to go over, please understand that simply by naming that, you can always then go to the definitions. Meaning, if I talk about definitions in here, that's like the heart of what a thing is, and that's where I want you to go to be able to explain it, okay? So what is the definition of velocity? Right there. Okay, so what is 8 meters per second mean? Right, your position will change by 8 meters every 1 second. Cool, that one probably the easy one. And again, if you struggled with that, you can look right here. Position will change by 8 meters when time changes by 1 second, right? Okay, next one. This is probably the one that people struggle with a little bit more. Okay, to that point, I will also suggest when you're thinking about this that you instead think about the units in terms of 8 meters per second per second. Okay, and again, if you struggle with this, look at what I just did with this definition. What is the definition of acceleration? Change in velocity over change in time. All right, so somebody tell me. Okay, you guys have been answering a lot. I appreciate that. Let's get the answer from over here. What does that 8 meters per second squared mean? definition. The time will change by 1 second. The velocity will change by 8. Biggest mistake made on this equation by students that start to get into it a while is dropping this. I don't know what that is. That is not a thing. That is not velocity divided by time. For example, you would not take, if these two were in the same problem, you could not just take this 8 and put it here, okay? Because you don't yet know how much it's changing. For example, I could have a problem where I am at 8 and I stay at 8, in which case acceleration would be 0 because it hasn't changed. I could also be doing a problem where I start at 8 and then stop in, let's say, 1 second, in which case my acceleration, discuss quickly in your group, it should be quick, but let's make sure. If I'm going 8 meters per second and I stop in 1 second, what's my acceleration go? What is it? -8, because my velocity is decreasing by 8 in that 1 second. All right, back up over here. Now, let's discuss again back to why is this the case? You'll remember these triangles exactly. This guy right down here represents change in time. This guy represents change in position. And no matter where you grab those triangles on that, this is why you can grab any freaking point on a line, who the heck cares? You're going to get the same ratio always, 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 always. If we use the numbers that I just did, it should go up by 8 meters when the bottom goes up by 1 second, yes? But you never want to use this equation, number 5 on the quiz. You never want to use this equation when that is happening. Why can't you use this equation when that is happening? Yeah, if I go up by the same amount of time in both spots, boom, I go up a larger amount of displacement. So does it matter where I grab the triangle there? 100%. And best case scenario is what you're doing is remember that this definition is actually average velocity. Now, constant velocity is average, right? Because if you have a constant, it's going to be the average as well. So, but could I get the average of those? Sure. Does that help me? Not much. I have the average velocity here and the average velocity there. We can see that it's increased, but that's probably not going to help us very much, which is why we transitioned to instantaneous over there. I'll also remind you of something I talked about briefly when talking about this lab in this conversation, and that is, because it'll help today, tangent lines. This is called a tangent line. Let's use a different color. The slope of a tangent line is the slope of that curve right there. Real quick, guys, hopefully we've noticed this already. What is slope by definition? So whenever we want to take math and put it to physics, what we then do is we go, okay, just then what's on the y and what's on the x? What's on the y here? What is that? Position. So this slope of this guy should be change in position. And what's on the x? Time. Oh, look, we already know what that is. The slope is change in y over change in x. Change in y and change in x is change in position over change in time. And what, by definition, is change in position over change in time? And that adds to our understanding of why these shapes are what they are. What is the slope doing here, guys? Staying the same. So does it make sense that it fits with the toy car lab in which your velocity stayed the same the entire time? Yeah, on the other hand, this is also change in y over change in x. I don't care that it's curving. So is the slope still velocity here? Yes. But is the slope changing? Why does that make really good sense on this graph? Because you're accelerating, because the velocity is increasing. Now, if all of that goes away, please understand this real quick. This graph right here, excuse me, this graph right here is always going to be for accelerating. We said acceleration is always going to be constant in here, right? So either it's something or nothing. Your x versus t graphs will always look like one of these. Let's talk about X versus T graphs that absolutely can't exist and the respective superpowers that they go with. Okay, so in your group, I'm going to put up here 3 X versus T graphs that cannot exist. And what I want you guys to do is go, why can't that exist in real life? And what direct superpower is that associated with? Okay. Let's go. X versus T is, which is the first one? Okay, first one is this one. Okay. And then X versus T is this one. And then X versus T is this one. Discuss quickly in your group, why are those not possible, and what superpower does each of those go with? By the way, for some of these, there's like 2 superpowers that are technically the same thing, which you might not have realized is in fact technically the same thing, but we'll get to that. You guys got answers for all of them yet? There's not much conversation. Keep going, talk about it. I'm going to call my shot here. All right, let's start with the first one. Why can't the first one exist? Okay, so what technically happened here if this occurred? You teleported, yeah. You are in one location in no time. You can make argument of teleportation. Here's the other argument that you can make. You guys probably know this from math, right? How do the slope of those two compare? The 2 lines. In what way? Which one's what?
The top one is slope is bigger.
Top one's bigger because it's steeper, right? Okay. Now the steeper I make it, the bigger and bigger and bigger it gets. Yes? Okay. And for sake of later, what is the slope of that guy? 0. So this would be when your slope is 0. It would also then be when your velocity is 0, which makes sense because your position would not be changing, right? You'd have a position say, okay, that's not important. Okay. Well, it is, but we'll come back to it. What is the slope of that guy? Sort of. Yes and no. Okay. This is a very, 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 very big number. Okay. Let's just stick with that there. So if I go closer and closer to vertical, if we argue that it's not undefined, okay, what is it technically heading towards? Infinity. It's heading towards an infinite speed, or whatever the max speed in the universe is, 3 × 10⁸ meters per second. So this could either be teleportation, or you could also make an argument of super speed. That absolutely, technically, no time progressed, or a very, very steep one would be super speed. All right, let's go to the next one. Actually, we're going to skip to the third one because I'm pretty sure you know the superpower with that one, and the middle one is actually probably the hardest superpower to understand. But let's go. Last one. Why doesn't that exist? What is that? Yeah, and time travel is weird when you really think about it, because most time travel movies actually don't do time travel. They they do the time travel in between the scenes, like, hey, we're going back in time, and they're back in time, but they just go forward normally, right? So they actually don't go backwards in time. Most of them don't handle it correctly. So weirdly, time travel in all actuality, if you were time traveling, it would take time, sort of, but the weird thing in physics is when you discuss time travel and an object going that way on the graph, what it means is that you have to defeat causality. Causality means cause comes before effect, which is so obvious plain. I mean, that's all it would exist in this case. Spainhour drops it, the thing falls. Spainhour kicks a chair, it falls over. Spainhour slaps an administrator in the face, he gets fired. Okay, causality, all right? So if you do the opposite and you were to watch somebody do it, effect would precede cause. Okay? Meaning, like, you would get to your destination and then later you would leave. Okay? If you've watched the movie Tenet, and your brain has not been boggled into that's got a lot of that in it, like attempting to show you what that looks like. Reverse entropy, it's a whole thing. Fires, it makes stuff colder. We don't have to worry about that right now. But yes, also technically, according to math, you can't have 2 on the y and be a function because you can't be at 2 places at once. It's arguable on whether or not you could actually have 2 of you existing at the same time, but we're not going to worry about that for right now. Also, t-shirt, it's right up there. What do we want? Time travel. When do we want it? That's irrelevant because, time travel. All right, next, this one. What's the problem with this guy? What's the problem with the middle guy? Most people are good on 1 and 3. 2 they struggle with. Think about what we just said slope is. Let's start with the first half. What's going on here? Person's just walking at a constant velocity in the positive direction. Yes? Okay? And then what's here? What's the problem? Yes, Gabe. Correct. Meaning if you look at the definition of acceleration, did we just change velocity? Yes. How much time did it take? 0. Now, let's say it's not 0. Let's say it's very, 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 very small. This is a calculus idea, but we can deal with it. Okay, very, very small. That makes acceleration very, 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 very big. And until you recognize it, this right here, if you attempted to pull that off, I don't care what that speed is. You can be walking 2 meters per second that way and turn around and walk 2 meters per second that way. If it takes you 0 time, you will crush every bone in your body to powder, and it will no longer exist. This is super strength. Okay? If you don't believe me this is super strength, imagine that you're watching football. Okay? Some of you don't like football. It's fine. You've probably seen a clip of it. It exists. Okay? Imagine the worst hit that you have ever seen. A kind of hit that makes you, oh, I didn't even want to watch that. What was happening? Well, probably the person was traveling that way, and in almost no time whatsoever, they were traveling that way. And you went, that was a hit. That was a freaking hit because they did this and very, very little of that. But we'll talk more about that in chapter 4. Questions, concerns here? All right. Now, let's get to the heart of this. Okay, great, Spainhour, all that fun jazz. What do you want me to do with this? Well, what we're going to do with this is I'm going to give you a situation, and I'm going to ask you to sketch what the x versus t graph is going to look like. But it's not going to be quite as simple as everything you just saw. What the main thing that's going to happen is we are going to have about probably 3 to 4 accelerations. Now, in this class, we've said accelerations are constant. So what we will do here is we are going to piecewise these functions together. Okay? So I'm going to give you a situation. I'm going to let you try it, and then we're going to go over it. Okay? You don't like piecewise functions? Is that what the curving is? It's not that big of a deal. Okay? Piecewise functions are just basically slapping together 3 different problems. All right, here it is. You guys have already, by the way, been doing piecewise functions because every time you use a new set of variables, you're just looking at a brand new section, new acceleration, blah, blah, blah. So here's a situation. Let's do it very similar to what we did another time before. I'm going to stand at this location that I did before, but so I'm just going to go half. Okay? All I'm going to do is I'm going to walk across the front and just come stand over here. That's it. I'm going to start time the moment I took off. I'm going to stop time the moment I stop. Okay? First thing I want you to do in your group, how many different accelerations was that? Discuss. Ooh, we got to do something else. This is important. This way's positive, and this is 0. You got to do this first. This is 0, that way's positive. Go. How many accelerations? Zeros count as an acceleration. Correct. What was it? 3. Yeah. Speeding up, in the middle, and then slowing down. So what you do is you go, okay, what should that shape of that graph look like? I just had it, you big dummy. Where'd you put it? I'll grab the other one. It's kind of impressive that I can lose it like this easily. There's not that much. I'm somewhat organized. Here we go. So, you draw x versus t, okay? I'll help you with this first one, and then we'll do another one here in just a second. Okay, we'll draw x versus t. What should the first section look like? Well, the first thing that you want to ask is, what's the starting position? What's the starting position? In this case, it was 0. So I'm going to do another color here. Let's go purple. Okay. So I start here. I don't always, but this case I'm going to start here. Next, this is the one that people struggle with the most. What was my starting velocity? 0. So that is not why I start here. I start here because initial position. How does velocity appear on this graph? The slope. So what does that mean my slope needs to be? My slope needs to start at 0. That's kind of hard to spot, so what we're going to do is we're going to accentuate. I probably shouldn't do this anytime at all, but I'm going to accentuate that it's down here at 0, and it's definitely a 0 slope. All right, what's now going to happen to my velocity? It's going to increase in the what direction? Positive direction. So I'm going to make a parabolic shape up. When did it stop increasing? And that, by the way, this would be probably much tighter if I was doing this very realistically, but I want you to see the shape. I want me to see the shape. This should probably be much, much smaller because less time, but here's what you do. So when we switch accelerations to that constant velocity, okay, you draw a little line here and a little line here to represent that this is now, that's a piecewise function, and now we're going next, and what should the next shape be as I walk across the front of the room? Should be a linear line. Whatever the slope is when I stop here, should be the continued slope as I travel. I do not want to see this because you just represented super strength by that little guy right there. Okay? All right. So you'll notice right now we have 2 sections. Each one acceleration is for each section is for a different acceleration. All right. Now, what should happen to my slope as I come to a stop? What should happen to my slope as I come to a stop over there in that section? I was at positive, right? And it should do what? Go back towards 0. So this is also a parabola. It's just a negative parabola. Just a reminder from math, this is what a positive parabola looks like. And this is what a negative parabola looks like. One's very happy and one's very sad. It's a good way to memorize it. Anyway, this is all we're looking for. Actually, I do want that in red, though. So you show me the 3 sections in this case. How are we feeling about that? Pretty easy? Okay, let's do real quick. Let's have you guys practice with this. Let's have you do the number 5 from the quiz, where if you don't know it, just a person's out walking and then they suddenly stop. That's all you got to do. Actually, I'm going to make it a little bit more difficult, though. Ooh, I like this. Here we go. Okay, so let's actually, I got you. Don't worry about number 5. I'm going to do it here. We're going to do my setup here, okay? We're going to start right now, and then I'm going to come to a stop over here. Notice some important things. I haven't changed 0, and I have not changed the direction of positive. So once again, I start over here when I'm already moving, okay? I'm going to start over here. I'm already moving now. And we will stop at the moment I come to a stop here. See if you can't do that on your own. Be right back after these messages. Please feel free to work together on this. So, nope, there's no sudden stops here. There will be an acceleration if I stop. So I would argue if this is what you're looking for, there should be 2 accelerations, right? Because I I did not. This is also important. Notice when I started time. So do I technically have to start from stop? Yes, but that's not when I started time. I started time when I was already moving here, and then I came to a stop, and I stopped time the moment I hit stop over here. Oh, Lillian, you didn't get your quiz.
Yeah.
Sorry about that. Yeah, it's literally all your homework is. That's all it is. It's just sketching. Yeah. All right. So, in case anybody was confused, well, let me give the answer first, and then I'll go back and explain it. It should have been this. There it is. Okay, let's talk about Y. Number one, Y is position initial up here. I started at a positive. Yes? Why do I already have a slope? If you went back in time, remember I started time right here. If you went back in time, obviously I had to speed up to that negative. There would have been this if we had worried about my stop as well, but obviously no, that's not part of it. So yeah, I was walking, it's constant, it's constant, it's constant. What happened here? What happened right here? Where was I? What was I doing? I just crossed the zero, that's it, okay? And then, right here, what did I do? Slow down. Notice again, no acceleration, positive acceleration, right? How can I tell it's positive acceleration? Because the acceleration's happy. There we go, okay. Now, I'm going to move this guy. I want this to go elsewhere. Cut. New page. Do the thing. Paste. There we are. Because I want to use the other one underneath it. We're going to talk about the other two really, really quick. You're probably not going to fully understand them right now. Okay? And that's okay. Actually, we'll go back to the first slide. First slide. Okay. First slide. Okay. We talked about position versus time. So what we're going to talk about now. So what does it look like if it's a velocity versus time? It's not the same thing. Nothing about your motion is going to be on, nothing about your position is going to be on here. This is just worrying about the scale. Now, firstly, if I'm just going to put a generic line here, let's talk about slope. What is slope? Let's do change in y over change in x. What is on the y here? And what's on the x? So what is slope on this graph? Acceleration. Now, while we are not okay with position instantaneously changing, because we're not okay with velocity instantaneously changing, are we okay with acceleration instantly changing in this class? Yes. So you will see sharp points on this graph, and it's okay. X versus t, no sharp points ever. V versus t, going to happen quite a bit. Now, how do you do this? Let's reference, actually, no, let's just stick with what I just did. Change in t, change in v. Let's go back to this one where I walked over here, and I'm going to do it, and then I'm going to explain it. This is the position versus time. Here's velocity versus time. Same thing you do now is you check, okay, I don't worry about this guy anymore because it's not on the velocity. But what is my initial velocity again for this guy when I was walking across the room? 0. So in x versus t, it's slope. In v versus t, it's just the y-axis. So what I should do is I should start at 0. When I started here on the graph, it was because position initial was 0. Here on the graph is because velocity initial was 0. Does that make sense? Okay. What did my velocity do initially right here? You said this already, so just repeat it. It increased at a steady rate because all accelerations in here are constant. So there it is. What did my velocity do in this middle section? if I do this perfectly, I usually have these lined up so that these are like right on top of each other, and that's super helpful. And then what's my velocity do at the very end over here? Notice all slopes here are constant, which makes sense because slope is acceleration, and acceleration in this class is always constant. Also up here, you could notice a positive acceleration, Ninja Turtles, because of this curve. How do you notice that this is a positive acceleration? Positive slope. How do you notice that there's no acceleration here? No slope. And then negative acceleration over there. Okay? Last one I'm going to go over. And again, I know I'm going over these last ones too quickly. I want to give this to you over the weekend. I'd like you to try some of these, okay? At least like the first one or two on the assignment, maybe even a few more. Actually, definitely, hold on, what is it? The first page is all kind of introductory stuff. 3's not bad. Definitely try to do 4, okay? Definitely try to do 4. But this is the A versus T. Now, the great thing about A versus T in this class is A, acceleration is always constant. Yes? So if acceleration is always constant, how are constants drawn on a graph? Horizontal lines, okay? And you'll remember we said in actuality acceleration changes, but in this class we're going to say it changes instantaneously. Yes? So this was not okay. This shape was not okay on the x versus t graph because position changed instantaneously. Is this shape okay on the acceleration versus graph? Yes. So all this is going to look like, I'll try to do it real quick here so it's not easy. Hey, this is positive, positive. Hey, this is 0. Watch here carefully. You draw a horizontal line just to connect them. As a matter of fact, a different color is probably helpful here. I think I just did inverse of what it was before. That's not a great idea, so now. Let's try to get something else. Let's go. Okay. So it's positive. Then in the next section, it's 0. And then in the last section, it's negative. In the remaining 5 minutes, I want you guys to see if you can't correctly do the V versus T and the A versus T for that graph that we did there. And again, if I'd done this really well, I should actually have them sitting perfectly on top of each other, because watch this. If I have 2 shapes here from 2 accelerations, I should probably have 2 shapes on this one and 2 shapes on the next, occurring at the exact same time. So something should occur here and on the next one. I know some of you aren't, draw these little lines both on the shape as well as this. It will help you in the long run. And those are, by the way, vertical little tick marks. They're just there to indicate the different shape. Just give it a shot, try some. Certain things that'll help. A versus T and V versus T should never see curves ever. Okay, the only time a curve appears is on X versus T, due to acceleration always being constant. Almost. What you have here is going at a constant velocity. That's correct. And then you have them slow down. They're still going at a velocity here. So you just need to continue that. Perfect. There you go. Also on A versus T, I said this a second ago, it's just simply going to be just It's on or off, pretty much, is how you're doing this. It's on, it's positive. It's off, it's positive. If we get really specific, which I might a little bit at times, it's like, hey, it's more positive or less positive. But really, it's just on, off, positive, negative. Really is all it is. So, what should the velocity do in the first section when I was walking that way? Ooh, I'm sorry. I told a lot of you were right and you weren't. Small difference. I just realized it myself. I want to remind you to help you out. I started time here. Which way was I headed? I was headed negative. Yeah, so that's my bad. I totally misspoke to some of you. But here's what it should look like. I think you'll understand why. So for those of you who said yes, it's just the flip of it because you start off at negative, not positive. And then finally, acceleration. What should the acceleration be for the first section? It should be 0, right? And for the second section, it should be happy face, positive slope, positive acceleration. Because remember, I'm going in the negative direction, so positive acceleration, so it should just be this. Fist to 5, how do you feel about these right now? Okay, let's do this. I'm going to give you a sample one that I want, at least if you don't get the homework, I at least want you to try. I totally didn't check your problem today. Ooh, you're lucky. Okay, I'll try to do that Monday. Let's have you do this, okay? Starting with the, so if you forgot, good luck, but Monday. Okay. Starting with the thing in my hand, we're going to do an X versus T for me throwing this up in the air. We're going to start when it stops in my hand and I take off, and we're going to stop the moment right before it hits the ground. Do the X versus T, V versus T, and A versus T for that situation. We'll say the ground is 0 and up is positive. Again, you got the marker in your hand, throwing it up, letting it hit the ground. I'm not letting it hit the ground because these things break. What's up? Yeah, I regularly do, don't I?
Sometimes for when you record it, I think you just like send it out.
Well, I've posted it, I'm pretty sure every single time. I believe so. All right. If you have any questions, let me know.